Hi everyone, this is Maverick Paul, the chemistry guru. Now in this week's video, we want to discuss how rate constant and equilibrium constant change with temperature. So let's take a look at this exercise. One of the key production stages in the contact process is the production of sulfur trioxide. So the equation is given involving 2SO2 plus O2 to give me 2SO3. So this is a reversible reaction. Enthalpy change of the forward reaction is exothermic because delta H it is a negative term. So the rate constants of the forward and backward reactions are given as K1 and K minus 1 respectively. Question is asking what happens to K1, K minus 1 and Kc expression, my equilibrium constant, if the temperature of the reaction is increased. So we have a few permutations here. Later we will try to solve for that. The topic tested in this question is actually under chemical equilibria, since it is targeting equilibrium constant. But we also need to consider what happened to my rate constant involving K1 and K minus 1. So let us try to deduce what happens to my rate constant first. Now it's actually fairly straightforward. We have learned this under kinetics. Involving rate constant K is affected by two terms, affected by changes in temperature, affected by the activation energy. So in general, when there is an increase in temperature, we will expect the rate constant to increase, and therefore the rate of the reaction will increase. Because when there's an increase in temperature, the average kinetic energy of my reactant particles will go up, and we will expect there is a bigger proportion of reactant particles with energy greater than or equal to the activation energy. So there will be more successful collision, or the frequency of successful collision will go up, and therefore the rate of the reaction will increase. So basically, the higher the temperature, the higher the rate constant K. Now, the other term that affects rate constant K will be activation energy, the energy required for the reactant to possess in order for it to proceed to form products. If there is an increase in activation energy, the energy barrier to proceed to form product increases, so therefore it reduces the rate of the reaction, and the rate constant K actually will go down. And what affects activation energy in CDBus? Usually we will consider adding a catalyst, and when I add a catalyst, there will be a decrease in my activation energy. Then we will say that since there's a decrease in activation energy, we will expect an increase in the proportion of particles with energy greater than or equal to activation energy. Number of successful collision will increase, or the frequency of successful collision will increase, and the rate of the reaction will go up, and therefore the rate constant will also increase. So in general, the higher the activation energy, the lower the rate constant, and the slower the reaction. In this case, since there's an increase in temperature, we will expect temperature goes up, the rate constant will increase for both the forward and the reverse reaction. So K1 and K minus 1 is expected to go up. This is involving the first part, targeting rate constant K. Now how about deduction involving our Kc expression? Now involving Kc expression, what we will do is we will focus on enthalpy change of the reaction. When there's an increase in temperature, according to Le Chatelier's principle, the system actually will favor the endothermic process, because the endothermic reaction will absorb excess heat from the surrounding, cause the temperature of the surrounding to decrease, and you try to counter the change imposed. If I look at the enthalpy change for the reaction, forward reaction is exothermic, reverse reaction is endothermic, and we will expect when there's an increase in temperature, the position of the equilibrium is expected to shift towards the left-hand side, because it is favoring the endothermic reaction to absorb excess heat from the surrounding, causes the temperature of the reaction to drop, and try to counter this increase in temperature. So if the position of the equilibrium is shifting towards the left-hand side, basically what we are doing is we are forming more reactants. So the concentration of the reactant is going to go up, and I am using up products. So the concentration of the product A is going to come down. And what I can do next is I can sub this into my Kc expression. Now when we write down Kc expression and deduce what happens to the magnitude of Kc, when we consider shifts in position of equilibrium, there's no need for us to write down the Kc expression explicitly. That means we don't need to express Kc in terms of the concentration of SO3 square divided by the concentration of SO2 square and the concentration of O2 square, because by definition Kc is the concentration of the product raised to the power of the coefficient divided by the concentration of the reactant raised to the power of the coefficient. Now when we are considering shifts in position of equilibrium, there's no need for me to make it very mathematical. I just need to express it in this way. My Kc in general very loosely is just a ratio of product to reactant concentration. In this case, when the concentration of my reactant goes up and the concentration of my product decreases because position of equilibrium is shifting towards the left-hand side, correct? And we will expect the numerator, which is my product concentration, is going to come down. Denominator, which is the concentration of my reactant, is going to go up. I have a smaller numerator, bigger denominator. I will expect the Kc value to decrease. So Kc is expected to decrease when there's an increase in temperature. So basically, we have deduced both Kc expression as well as the rate constant. So what we can do is we can answer this question. The answer in this case will be option D. Both rate constants K1 and K-1 is going to increase while my Kc expression, my equilibrium constant term, it is going to decrease. Alright, so that was the discussion involving this question. And if you have learned something useful from this video, please give me the thumbs up, like this video, and subscribe to my YouTube channel for more weekly video lessons. That's all for now. I'll see you next week.